Hello, good afternoon, everyone. Good evening, sorry. It's already evening now. Let me open the slides. So this one, I guess I have finished this one. All right, so today I guess probably will be our last lecture this semester. Since next week, it will be the term that you guys need to start to present your project. Okay, that's the class project presentation for week 12 and 13. And in week 13, I will take some time to do the course review. Okay. So basically that will be the arrangement in the coming weeks. Any questions and comments? So I guess you guys must have questions about the presentation order. So I will do the random draw based on the submission of group information on Canvas. So I will first record down how many groups are there and draw the order for you guys. And I will announce the order of presentation before the class next week. Okay. So so that all of you guys will need to prepare the project. So how long will the presentation be? I can't remember. Did I make such kind of statement in the project specification? No. I bet it will be like 12 to 15 minutes for each of the group. Yeah, for your presentation. I will make more clear notes on Canvas, announcement on Canvas. Yeah. You feel too short or you feel too long? Maybe 12, not even 15, because we have too many people in this class. So we may have like 20, about 20 groups. Okay. So every group is 12 minutes. And if we don't take any break, then that would be about like 4 hours. I bet it would take like 5 hours. And I also need to use 1 hour to do the review because we have the final examination. Okay. Oh, this is very important thing I would like to share here about the final examination. So based on the information so far I've received from the university, the final exam will be on campus. Okay. It's the default mode of the final examination of this course will be on campus. So far, I didn't receive any other notification. So I have prepared the question paper and also submitted to the university. Okay. And all the things become very formal and normal as they passed. You guys probably will be arranged in the gym, which is a very large space, and to do the final examination. Okay. And the additional information is that if some of you cannot really make the trip to Hong Kong, you guys need to raise such kind of concern to the school and to apply for the online exam. And the university said they will help arrange such kind of thing, but I don't know how. But anyway, they will help. I bet there will be two solutions. One is for the online exam students, you guys probably just receive pass or fail grade. Okay. And for the others, attend the on-campus exam, can receive letter grades like from A, B, C, D. okay? Or I don't know. I personally don't like online mode mixed with the on-campus mode because I feel that would be unfair, okay? Although this exam will be open notes and open book, you guys are welcome to take the class notes printout with you to do the final exam. But the online ones, we cannot prevent the communications, okay? So that will be one risk. So I will think about the penalty applied to the online exam mode. But anyway, I will first listen what the university will say, then I will follow the standard, okay? But what I should announce here is the final examination will be on campus by default. So far, I didn't receive any updates, so that indicates it must be on campus, okay? Now, during the exam, the only electronic devices that you guys can bring in will be the calculator, okay? Computer and iPad are not allowed, all right? So far, so good. Any comments, questions? Last time we probably stopped at here, right? Only paperwork allowed. What do you mean by paperwork? Yeah, so I bet you mean that you will need to write down your answers on paper. Yeah, that's true. Yes. You will be given the answer book and you need to write down the solution. Okay. It's like, yeah, what you have done in your past. Okay. That the question paper will be dispatched and the answer book will be dispatched and you need to write down the solutions on the answer book. No, there will be no past papers or references. But I would, in a review, I will tell you guys what will be tested. It will be very clear scope, so can help you better prepare for the final. Okay, so if there's no more questions about the final exam, and also the next week class project presentation, then let's go through the remaining class slides. Okay. So last time we stopped at the using different machine learning tools to analyze the power curve, to do the power curve modeling. Okay. So we will like to incorporate such kind of power curve modeling into the estimation of the power output of a wind power generation process. So we will see like how the physics-based models and gradually turn to kind of physics-informed data-driven model and finally data-driven model, okay? So the first one, if we look at the left side, this is the very classical aerodynamic model describing the wind power conversion process. Its components include a constant, and this rho is air density, pi is 3.14, and R square is the area swept by the wind turbine rotor, and this is the power coefficient, multiply the cube of the wind speed. So this aerodynamic model is very clear. The only unclear part is the power coefficient, which is a non-parametric function describing the relationship between the power and the tip ratio, tip speeds and also the blade pitch angle. Okay. So this one is not parametric, and we don't have its explicit form. And the initiative or intuitive way will be, if we have the data, we can fit such kind of power coefficient function based on the data. So if we have the observation of the power and all the others and are the known factors, the R squared, rho pi, we typically, the L density we typically assume as a constant, and the wind speed is also observed, then we can, using the observed power, divide by those terms, multiply together, and get the value of the power coefficient. Okay. Then based on the value of the power coefficient and the observed rotational speeds, omega, and also the wind speed, blade pitch angle, and historical records of power coefficient, we can do a fitting of the dynamic model describing the relationship between the control factors, system dynamics, and the current status. Okay. Then we can rewrite such kind of power output model based on such kind of replacement of the non-parametric power coefficient function with these data-driven components. Okay. The very funny thing is the wind speed here is something that we don't know. Okay. And also the measured wind speed is the wind speed passing through the wind turbine already, because you guys remember the anemometer. It's in the previous slide. The anemometer is no, it's in this slides. This notes. I remember. No, the previous one. Sorry. The anemometer is sitting on the back of the turbine. Okay. So the uncertainty of wind speed we cannot control in the future, but we can, according to the historical records, we can write down a Markov model to describe the state change of the wind speed over time. Okay, it can be converted to a static Markov chain. Okay, and it expressed as a transition matrix of the wind speed, like after 60 seconds. Okay, so we will see that based on our data and the statistical analytics, if the wind speed is at the low level, it is highly likely that it will stay at low level. And if it is at high level, it will be highly likely stay at high level. But if it is in between, then you will find out its likelihood of staying at itself states will be decreased a little bit. For example, if the wind speed is a kind of jump into the cutting, higher than cutting state, it becomes 60% likelihood that it will stay at its previous state. Otherwise, other chances are like moving higher, okay, or moving a little bit lower. The most dynamic part is the wind speed at 7 to 8, 8 to 9, and 9 to 10 state, 10 to 11, 11 to 12. These states, they are very, very dynamic. Okay, they will have quick changes in the next time step. But based on this transition matrix, we can do a kind of stochastic model, okay, by multiplying the likelihood of the wind speed, and we can obtain the expectation of the power output at the next step, okay. So this data analytics also can give us some help of the power estimation. And the second approach to do the wind power output modeling is purely data driven, okay. So we have the observed power, we have the observed wind speed, we have the observed torque and blade pitch angle to critical controlled parameters. We can directly using this one as y and this one as x to pair those data points and to fit the machine learning model and make it as a regression problem. Okay. But this one has a drawback, which means it does not contain, it does not consider system dynamics. What is the system dynamics? The dynamics is usually described that the current status of the output will be affected not just by the current states of the control and uncontrolled parameter as well as its past record. Okay. If you have a PA T with a function of T minus 1, then these historical outputs in terms of the relationship with this current power output indicates a kind of dynamic changes. So this is dynamic. So a more complete model will be like this. So you can see the dynamics of the system. Right, so this is some of the tables describing if we consider pure data-driven modeling problem, then the very famous machine learning shallow models that we can consider, including the artificial neural network, boosting tree, random forest, full vector machine regression, and k-nearest neighborhood regression, and what are their performance. So in this application, we discovered that the neural network regressor actually is one of the best. And the three modeling strategies, we figure out the second modeling strategies might be the most useful one, okay? So we can actually do the multi-period prediction by rolling forward your observations or directly using the multi-step ahead future observations to build up the data-driven model. Okay. So the in-class practice will be using VECA. So I guess the TA in the previous lab tutorials must have taught the VECA. But I remember some of you said that your Mac operation system cannot install the VECA, then you have to go with R or Python. Okay. Let's wait a while because my Adobe system in this classroom desktop needs to be updated. I cannot open that PDF. Yeah. All right, let's look into the third part of this data analytics application. Continue. So in the previous class notes, we talked about just like modeling, okay, using machine learning techniques. But in this part, we are going to extend such kind of topic by incorporating some of the other methods into machine learning and make a more comprehensive framework, which will do a more interesting analytics task. First, we look at the machine learning plus control. And next, we talk about machine learning plus operations optimization. And last one, we talk about the machine learning plus condition monitoring. So first, let's look at the control problem. So the wind turbine control is very straightforward. There will be two things to be controlled. One is the generator torque, you need to, the controller will write down the control settings of the torque time by time to control the wind turbine. Another is the pitch control. And the signal to determine the control settings will be include the external wind speed determined high speed shaft velocity. Okay, this is the rotating velocity. Okay, and as well as the power output of the turbine. Okay, so the high speed shaft velocity is very highly correlated with the power output. So it becomes a feedback. For example, you want to maximize the power. You want to maximize the speed of the velocity of the high-speed shaft. Okay, you want it to always rotate quickly, fast, so that the generator will rotate fast and to generate high-quality power. Okay, and you don't want it to change dynamically over time. You want it to keep its maximal coefficient, maximal efficiency in terms of the generating of the power. So if we look at the traditional PID control, then there will be one strong issue is first, the system signal feedback is already have a delay. Okay, that means the future needs. So this signal only returns the response of the system after your previous settings. Okay, now your new settings needs to encounter the future situation. But if you just rely on the previous feedback, system feedback, then you got a big error. Okay, you got a big error. You got a big delay in terms of the situation. So what we have learned in the past is we have the data-driven model. First, the first advantage is it overcomes the assumptions made in the traditional aerodynamic models. Okay, it directly fitting into the data, so it mimic the real situation. And the second is based on the data-driven model, we are able to offer some anticipation capabilities. Okay, so we are able to study the anticipatory control of wind turbine. That means we have some future forecasting. Okay, then based on the forecasting results to optimize the process. So mathematically, the wind power generation process can be represented by a triplet, which is x, v, y. And here the x denotes a vector of controllable parameters, and v denotes a vector of non-controllable parameters, and y is a vector of response parameters. Okay. If we give such kind of notation, then the problem will be simple. First, we do the modeling. We want to build up the relationship between the response and the controllable and non-controllable inputs. So we have y equal to a function of x and v. Okay. The next step is very obvious. We want to estimate such kind of function f. Okay. So basically, it's a function estimation process and identification process. So such kind of process also needs to rely on traditionally based on the starting system dynamics and now from data. Okay. So the function can be described as this. So this one is the vector y. Okay. And this one plus this one, they are v. Okay. And this 4, they are x. All right. So why it's like it looks like this? First, the model needs to consider the dynamics. Okay, so that's the historical system state and the non-controllable external factors, the wind speed and the dynamics of the wind speed. Okay, so basically VT and VT minus one, the current and one step back historical observation, they form a kind of dynamics. So these three, they are not controllable, so they are non-controllable. Okay. So others are the controllable parameters, x1 and x2. One refers to generated torque and another refers to blade pitch angle. So we also include the current settings and its historical settings. Its historical settings are not changeable, okay? You cannot change the historical settings, but you can change the current settings, all right? So this is called modeling the system dynamics. But what if we want to make it has a predictive capability? We make the time value move one step forward. Then we will have y1t plus 1, which is equal to y1t and x1t plus 1, xt, x2t plus 1, xt, vt plus 1, vt. Then what will be different? We have the observation, at time t, we have the observation of the power output. We have the observation of the wind speed. We can use forecasting model to forecast the one step ahead wind speed. We can control the setting of the two controllable parameters at t, and we will predetermine the settings one step ahead, okay? So this one will be adjustable. Then we are able to determine a combination of the dynamics of the future control settings to lead to a kind of anticipatorily controlled or maximized power output in the future. Okay. So the wind speeds can be predicted via a time series model, as we have said. Okay. So these slides we can skip. Okay. Then next we will talk about the optimization. So in this study, the authors discuss the optimization of the power output at the current step and the power output one step ahead. So that enables a kind of anticipatory control capability, as well as the rotor speeds and the rotor speeds one step ahead. So there are two issues. One is we want to maximize the power output, and the second is we want to smooth the change of the system states, okay? So what we can control is the controller at time t and its future, okay? But the question is, such kind of model, they are data-driven. They are non-parametric, okay? Then the future, next we will talk about to solve such kind of model, we need to rely on the computational intelligence solution techniques. But next we will talk about the reformulation of the objective. Okay, so in this control, we are very, our objective is very straightforward. We want to maximize y1 and y2 at the current time and one step ahead. So we can do something. We can first do a linear combination. of the power output we want to optimize. Okay. And we know that the maximal capacity of the power output of a turbine is 1,600, which is according to the specification of this machine. Okay, the model of this machine after manufacturing. The manufacturers said like its best performance will be 1,600. Then we use Y1T minus this value, Y1T plus 1 minus this value. Okay, then we get the difference. And based on such kind of setting, we can change a maximization problem to a minimization problem. We want to minimize the difference. That means we want to drive the power output to be as close as its maximal capacity. Okay. So this is one trick of the problem transformation. The second is we want the rotor speed to be changed smoothly. Okay. We don't want the machine constantly rotate at kind of 500 like RPM, but at the next time it needs to be sharply increased to 1,000, double its rotational speed. That's not good. It will make very harsh changes to the machine and will damage the machine health condition. So we want the difference, okay, between the states to be smooth, okay? Then we minimize the difference between such kind of changes. Then we change a kind of maximization problem to a weighted, linearly weighted minimization problem, okay? We also need to refine the objective functions by integrating the estimation from the aerodynamics model. And this is the incorporation of the domain knowledge. So for example, we know that the maximal capacity of a wind turbine power output will be 1,600. And this y-axis is the power output. This x-axis is the wind speed. We know the wind power curve model, right? But we also know the Betz law. The Betz law says like when a wind speed is less than the rated wind speed, the wind power generation have an upper bound. And this upper bound can be briefly described as 2.625 multiplied by the cube of the wind speed. This is estimated based on the aerodynamics model, the physics constraint. Why we want to do this? Why we need to set an upper bound? This is basically because the model we considered for estimating y, they are data driven. So they might have errors, and at some values they might have very misleading noises in the output, which will give us very ridiculous results. And if such kind of results, we believe it is true and put it into the machine, then the machine will become very unstable. So we need to give a theoretical bound to bound the output of a data-driven model to guarantee that its results will be within a safe zone, okay, a safe zone. So this is the incorporation of the domain knowledge into the formulation of a machine learning problem. So we're incorporating such kind of refining the objective function by incorporating some of the domain knowledge as the input. So the whole optimization problem formulation will be like this. Okay, we have the objective function formulation for this number of y's, and this j is the objective to be minimized, and the expression of the j of the objective function j has been offered in the previous slides. Then we also need to consider a number of the constraints, okay, basically including the controllable the constraints for limiting the value of the y, the output, and the controllable parameters. So this model is quite complicated and involve a lot of data-driven forms. And to solve such kind of model is pretty challenging. And there are two reasons. One is the data-driven models, they are non-parametric and nonlinear. So it is very difficult to apply the explicit optimization solution to have a closed form solution for that optimization problem. And it is very difficult to find one existing exact solution methods to address such kind of problem. So we have to solve it with the heuristic search aspect, which actually does not require any explicit form of the optimization model. So in this paper, authors apply the evolutionary strategy algorithm. Okay, so basically it's a heuristic process. The general idea is you initialize a number of candidate solutions for such kind of optimization model, and you do changes, okay? So the individuals is defined like this. The Z is the value, candidate value of the controllable parameters, and the sigma is the degree to mutating them, to change them iteration by iteration. And finally, you closely approach the best solutions. So in this problem, the authors, because they are using heuristic, so they can change a single objective back to a bi-objective problem formulation. So they can determine the best solutions based on the Pareto frontiers of the candidate solutions. So they apply a strength Pareto evolutionary algorithm. Okay. So I won't explain too much about the evolutionary algorithm. If you guys have time, you can spend some time to learn. It's very simple. It's just some heuristics. For example, it's kind of a better version of exhaustive search. Okay. For a problem that you don't have its explicit form, the most stupid way would be, okay, I exhaustively try all its possible solutions and find out one which works best, right? So that's the exhaustive approach. But the better one is, how about I initialize some? I select a subset of the solutions, and I base on some better ones in these subsets, and to do some kind of changes of those better solutions, and to gradually move them towards the best space, okay, the optimal solution. So if in this problem, if you have a set of candidate solutions and you want to make changes to them to do a kind of search of other solution space, the mutation process will be like this. So you have the current iteration of solutions, you evaluate it, you find out it's probably good. Okay, then how can you change this to explore like other solutions? You can add a noise. Okay, you add a noise into the current solutions to give it a new value and try to see the newly added updated values will give you a better results. If yes, you keep it. If no, you drop it. Okay, so this is basically the search process. So it will be done iteratively and finally returns the best solution. And the previous mutation process is a kind of tiny changes. So for example, I need initial solution, which is 3. I replace these three, or I fit these three values into my objective function, I find out it can result in an improvement. Then based on this normal distribution, it returns a kind of random value 0.01. Then the new solution will become 3.01. Okay. Then I fit it into my optimization model and to try whether the objective function value can be further improved. If yes, then I keep 3.01 for the next iteration of search. If no, then I return back to 3, try another value changes. So if you think let me draw a contour of the optimization. Assume the global optimal is here and currently your solution is here. So the mutation process gives its capability to explore around the very near neighborhood space, okay? But this kind of exploration, or sometimes we call it just exploitation, okay? Exploit, that means explore with a small degree, okay? Sometimes we think the current state is still far away from the global optimal. Then how about we do big changes? So that's the recombination. Assume there's a new candidate solution, which actually at the same latitude, okay? So that means they have the same optimality, similar optimality. Then how about we have a recombination and to make changes and search some of the points here. Then this one probably have a better degree. Okay, then we found it, then we move towards the global optimal. So then you need to consider next is the recombination of the parents. It's just take two parents, take an average, okay? Or take some parts of the parents to do a combination. All right. So we stop here and we take a break and we come back, okay, after break. Okay, let's come back. So first, let me make an announcement about the class project presentation. I will fix the time to 12 minutes. 15 minutes will be too long. You won't have that much time. Okay. And all group members need to participate in the presentation. So you cannot just send a representative to do the presentation, okay? The order of presentation will be randomly by me and announced right before the next class. Okay, any questions? No, then I will do this. Okay, so I have made the announcement of our class presentation next week. Oh, I forgot to share my screen. Yeah, so we will start our class presentation since next class on November 18th. And each group will have 12 minutes and plus 1 minute Q&A if possible. So if there's no problem, then we can skip this 1 minute Q&A. And all group members need to participate in the presentation. And the order of presentation will be randomly drawn by me and announced right before the next class. Okay. All right, so yeah, so we have actually briefly introduced the main idea of the evolutionary computation for optimizing this non-parametric optimization model. And it's kind of rolling forward process in such kind of turn of optimization in real process. That means we obtained one set of the optimal X, then we implement it, okay? Then we re-optimize to get the another X, another optimal control parameter, then implement it and rolling forward. Yeah, every member needs to speak in the presentation. So this one will have two advantages. One is everyone will have a chance to practice. Another, we can prevent the free rider. Okay. So this is the computational results of the original settings and optimized settings of the wind turbine control. You can see this is the previous observed settings of turbine control, and this is the optimized. So you can see the gap and the improvement here. And this is the rotor speed and previous setting of rotor speed. You can see a more smooth control of the rotor speed after the optimization. So this is the intelligent control based on the data-driven models. And next we will talk about the data-driven wind farm operational optimization. Okay. So basically, if we consider the wind farm optimization, then the unique contribution of the data-driven model is we are able to model the heterogeneous characteristics among wind turbines in a wind farm. So what does the heterogeneous characteristics of wind turbine mean? That means the different factors of that wind turbines. Okay. I guess I can accommodate this request if you work overnight. Yeah, so you guys can present on 18th. Okay. All right, so optimizing control of all wind turbines in a wind farm simultaneously means the wind farm operational optimization, right? So actually turbines, they have different characteristics. This is due to even they are with the same model due to the different installation skills of the workers and the locations they sit, they will have different generation performance. Okay, but what we want to do is we want to actually optimize their performance in terms of generation so that we minimize the cost in operating a wind farm. So besides the operational optimization, what are the other factors that we need to concern in the operations? Okay, so first we need to concern about the costs and the power production, which can be converted into cost two. For example, we want to maximize more power. We can use 1/P to indicate a term of the cost to minimize this 1/P. Okay, then actually indicates the maximization of the power. Then we need to determine operational decisions, which means the on and off of the system as well as the control settings. We also need to handle uncertain factors, including this. We are using the stochastic or robust optimization. So our operational decisions will include two types. The first one is the binary decisions indicating the on and off of those individual distributed machines. And second are the control factors of those machines, okay, if they are turned on. So we have some definitions of the cost need to be considered. The first is the cost of operating a wind farm in power generation, which includes the power shortage cost. That means your power generation, the power supply cannot meet the demand of the power grids. And the operations and maintenance cost. So your machines might face problems. Then you need to send people to inspect and fix those problems. Those are the costs. And the idle turbine cost. So the idle turbine cost is kind of opportunity cost, okay? If there are wind in the environment, but you didn't turn on your wind turbine to generate power, then you are wasting the chance of producing electricity and making money, right? So that's the idle cost. So the opportunity cost reflects the potential revenue of selling the amount of electric power equivalent to the power shortage, okay? And the compensation cost is the penalty paid to activate backup power generation system or purchase power from the third agent. Okay. If you are shorting power in terms of the supply, you have to buy some extra from the third agency, or you need to turn on the backup power generation units, including your energy storage systems to discharging the power to the grid, or you turn on the thermal generators, okay, to a higher speeding level, to generate more power. Then by consider all the cost factors, we can write the objective function which describe the total cost of operating a wind farm as follows. We can have the operating cost here, compensation cost here, operations and maintenance cost here, the idle cost here. Okay. So basically, the compensation and opportunity costs, they are actually related to the delta, which is the shortage of the power. And operation and maintenance cost is a linear coefficient, go with the amount of power you produced. And the idle cost is actually the chance that you didn't turn on your wind turbine to sell the power to the grid, which the B here, I guess, is the electricity price, okay, and multiply the amount that you should generate at that point. So we inherit the previous data-driven power output model from the previous studies. Okay, we use the control parameters and predicted wind speeds to estimate the power output. We make a simpler version. Then we build up a deterministic version of the operations optimization model, which the objective function written here, and the others are the constraints, including the decision variables and the non-controllable variables and other data-driven models here and so on. So based on this base model, the computed decision-making is deterministic with the input of the data. So to better handle the uncertainty in terms of the wind speeds, we can actually formulate a stochastic optimization version of such kind of model. We will take the previous Markov chain-based transition matrix of the wind speed here. We calculate the conditional likelihood of the wind turbine in the future state, in different future states and condition on the current observations. Then we, based on the data, we can generate such kind of transition matrix of the wind speed. Then we can multiply such kind of conditional likelihood of the wind speed with the cost under such kind of wind speed scenario, and to get an expectation of the power generation. Then we will find out in these terms, okay, then we can get an expectation of the total cost. Then we will, based on such kind of expectation, generate a more robust, more anti-risk decision-making in the wind farm operations decision-making. And the previous problem formulation is a mixed integer nonlinear programming problem with data-driven components, which is very difficult to solve. So we developed a new heuristic called migrated particle swarm optimization. Okay, so actually we integrate or migrate the GA genetic algorithm operator to deal with the integer part in this nonlinear programming problems, and the particle swarm optimization part to deal with the continuous variables in the nonlinear programming. Okay, and so that we introduce a kind of capability to escape from the local optimal. Then based on different types of model, then we can calculate the cost associated with that model. So this BS is based on the benchmark, okay? So we will find out that different decision model were associated with different values of the cost, okay? So our model can offer the optimal one, the best one compared with some of the benchmarks. So the previous one is talking about using the stochastic programming to do the decision making in a wind farm operations optimization. The thing is, we need to discretize the wind speed to a number of discrete scenarios, okay, and compute the expectation. But how narrow down we should discrete the wind speed to that kind of scenarios is a great problem, because if we divide a lower interval of the wind speed scenario, then the computational cost will be pretty high. Okay. So can we have a more flexible way of dealing with such kind of uncertainty? And we can have a problem formulation can against such kind of uncertainty, okay? And also facilitate the computation. Then we study a robust formulation of such kind of operational optimization problem. So in this problem formulation, we are able to consider more uncertainties rather than just the wind speed uncertainty, okay? So we describe the uncertainties in the wind farm operations decision-making involves two types of, or two levels of uncertainties. The first one is called operational state, which indicates that the wind turbine states will be degraded or will be changed over time, okay? So it will affect the efficiency of generating power. So such kind of risk will be incorporated as the uncertainty set construction. And we call this part is the operational state uncertainty. The second part is the power prediction uncertainty, which involves any power prediction error, okay, uncertain power prediction error. So we integrated these two types of uncertainty and describe the uncertainty sets, U1 and U2. They are basically the same thing, but U2 will introduce a kind of budget allocation factor, this pi here, to control our budget of uncertainty, which can be handled in this optimization problem. Now we still do the minimization of the cost, but subject to, with the data-driven components, but subject to the uncertainty set formulation. And to solve such kind of problem, we introduce two levels of heuristics. First, a robust optimization is a max-min two-level formulation. And we first do the problem simplification. We relax the max part and we study the minimization part first, okay? And then we introduce the PSO, the particle swarm optimization plus the barrier methods to solve such kind of problem. And with a more analytical probability guarantee in the solution quality, okay? So the optimization part can be a little bit mathematical. difficult to understand. But next, we talk about the condition monitoring. Probably is a little bit more straightforward. So in this condition monitoring parts, we are gonna to introduce two types of applications. One is the system condition monitoring based on the SCADA data, which is the numerical data. And another is the condition monitoring based on the image data. So again, we look into the wind turbine condition monitoring problem. Okay. So while we need to study the condition monitoring because failures of such kind of machine can be very catastrophic. For example, if your turbine has a blade breakage like this, that means a long time delay. This is already a good case that your machine is not broken. Okay, it's just blade break. So it will take quite a while to replace the broken blade to make the wind turbine return to normal. There are other cases that the wind turbine blade break when the turbine is rotating. Okay, then the braking components were flying away and probably will cause fire hazards in the environment if there are a lot of trees and grasses. Okay, and also the flying blade might hit the tower and make the whole wind turbine destroyed. So one important problem we study is, can we use the conditional data collected based on the wind farm SCADA system to monitor, to predictively monitor the potential blade breakage event? Then we introduce an autoencoder based signal dividing. So one challenging question is, for those mechanical components, its conditional state is not supervised, directly supervised by a SCADA system. That means your parameters or your attributes in your database, none of them directly relating to the health condition of such kind of component. And what we do is we think if that component has a healthy problem, although it is measured, but such kind of machine is a coupled system, its problem will be propagated to the value of attributes, other attributes in this system, right? Then that's why we're using the denoising autoencoder to derive the full mathematical mapping between all the attributes in the wind turbine and to do such kind of risk reconstruction. Okay, so we're introducing a stacked denoising autoencoder to deriving a health indicator. What our aim is to learn the mathematical mapping between its raw inputs and its reconstructed input. We believe we hypothesize that there must be such kind of stable relationship or stable mappings between these two signals. So if it is in the normal condition, such kind of mapping will be stable and will not significantly change. But once the system got problem or something very big gonna happen, then the whole mapping in terms of the mathematics will be changed. Okay. So rather than directly measuring or monitoring the health signal of a wind turbine blade, which does not exist in the world, we then monitor the errors between the input X and reconstructed X. Such kind of error will further reflect the mapping between the X and the X hat is stable or not. So based on the derived reconstruction error as the health indicator, we apply the EWMA chart in a statistical process control to build up the monitoring decision boundary for such kind of indirect health indicator. Then we will build up the decision boundary, okay, for monitoring. And we tested turbine with normal conditions and turbine with blade breakage happen in the future. We will find out we are actually able to predictively identify the potential failures a couple of hours ahead of its true occurrence, which will help the turbine to receive an early alarm that the turbine is going to have a disaster failure, so that the wind farm can prevent such kind of failure case happen. Okay, so this is condition monitoring based on SCADA data. So the next is we're going to discuss the condition monitoring based on the image data. Okay. This is an application we are studying using the drones or unmanned aerial vehicles to take images of the wind turbine blades. And we would like to do from the computer vision perspective to identify the cracks born on those mechanical structures to help with the routine inspection of the wind farm. So we propose such kind of two-phase computational framework to do vision-based wind turbine blade crack detection. So the first phase is a kind of data pre-processing. So we identify the negative samples and positive samples so that we will allow our algorithm to filter out the backgrounds from the cracks. Okay. Then next, we apply a handcrafted feature template, which is called highlight features, to extract features from background and crack images, the negative and positive images. And those features will become the decision-making support factors and fit into the cascading classifier to determine whether the image contains crack or not. Okay. So this slide shows the highlight features. How does it look like? It basically includes different templates, a number of templates to do the contrast comparison. Okay, the contrast of the pixels in different regions to extract patterns of different patterns in image data. So this is a cascading classifier. It is a very interesting architecture. It's a sequential decision-making process. It is composed of a number of strong classifier, and each of the strong classifier is a number of ensembled weak classifier. Okay, so it adopts the overkilling strategy. So if we fit the highlight features into a classifier, and it said it is not a crack, then we save the efforts of the following. We directly say it is not a crack. So we recognize an image contains crack only the data can passing through all the decision-making process, all the stages. Okay, then we say it is positive. So this algorithm can do online, can be executed online, and its performance is great. We can show like different cracks we identify through the wind turbine, even with the very tiny ones. Okay, so that's we basically finish the wind energy application discussion. So next, we're going to go through some of the building energy saving applications. Okay. So if you guys apply for the kind of ground AI challenges organized by the EMSD Hong Kong, then you are actually doing something closely related to these slides. So actually, we are going to explore the domain knowledge of what is the major energy consumer in a building and how this is dynamics and how we are going to model such kind of system and doing optimization. Okay. So first, let's look at the building energy consumer, major building energy consumer nowadays. So if we exclude the electric vehicles, then the most commercial buildings or skyscrapers, they are actually equipped with a very major component, which is called heating, ventilating, and air conditioning system. So in abbreviation, we call it HVAC system. So this system has the function of heating in the winter. Actually, in our building, we do have one, but we just have air conditioning. Hong Kong does not need heating, actually. We do have ventilation. Okay, our system do have ventilation because you can see that all the windows, they're closed. Okay, all the windows are closed here. So the internal and external, actually, they're isolated, separated. But how does the air got exchanged? The fresh air is exchanged via ventilating process. And definitely the major function of our system is called air conditioning. We do cooling in the summer. Okay. And besides HVAC system, another big energy consumer is our lighting system. Okay. And then other electrical appliances, and last one, electric vehicles. So according to the statistical results in the past, in different regions, different buildings, people all agree that the HVAC system actually take the most share of the building energy consumption. Okay. And this kind of consumption making us a comfortable environment to stay. So each of the HVAC system, they try to control the room temperature between 68 degree Fahrenheit or maximally 75, okay? And it is actually 20 degrees Celsius or 25 degrees Celsius. It's 20 to 25 degrees Celsius. That's the temperature. And the humidity in room needs to be controlled between 30% and 60% relative humidity. Okay. So humidity too low, we feel too dry. The humidity too high, we feel too humid. Okay. And the air pressure also needs to be slightly controlled, slightly positive to reduce the outside air infiltration. And rooms typically have several complete air changes per hour. So actually the ventilation is down once, okay, per hour, okay, or a number of times per hour to make sure that we have sufficient fresh air inside our building. So this is how the HVAC system working in a building, okay. So actually its components distributed into different levels, but the main mechanical and electrical components are inside, typically placed on the basement. So including heating and cooling components. Then definitely we need to have chambers to do the water delivery Okay, once you have, air delivery. And we also need to supply cooling and heating water, okay, to do the temperature exchange between the air, okay, and the thermodynamics. And this is the typical HVAC system chamber, okay. The air flowing through, it has air pumps to pump air, okay, from the chamber, from the outside chamber and to the internal exchange, okay. So for HVAC system, we have a number of major components. The first one is called mechanical room. So typically it's here, okay. So this mechanical room, you can find out that in every skyscrapers or tall buildings have HVAC systems. It has such kind of mechanical room. So in this room, it will have boilers, not in Hong Kong, but in other area. Probably some places in Hong Kong, it has heating capability, then it has boilers. And chillers, definitely. Okay, this is for cooling air, and pumps and heat exchangers. Okay. And in every floor, or in some of the major rooms, we have air handling units. Okay, this air handling unit has following function. It can do heating, can do cooling, it can do humidifying and dehumidifying, and ventilating, filter, and distribute the air. Okay. And we do have room controls for every room. It includes a thermostats, measure the status of the room, and also have a variable air volume boxes to do a kind of tiny adjustment of the condition on the room. So this is how the boiler looks like. This is how the chiller looks like, okay? And the mechanical room contains a number of boilers and a number of chillers, okay? And the chillers typically connected in parallel, okay, and boilers too. And what they do is they do water cooling or water heating. Then the water will be supplied through those pipes into the air handling units to exchange the heat of the air in the room, okay? So basically, this is the working flow of a heating system. So you have a boiler. So this is water comes back from the air handling unit. You have boiler, you heat the water, and the water flow through the air handling unit. And it has a hot water valve to control how fast the water flows through the pipes, okay? And how fast the water circulated. Then you have hot water coil here, okay? And it will do the heat exchange with the air in the room to heat the air actually, okay? And this is how the cooling system works. It is similar as the heating system. You have a chiller, okay? You have a chiller here. Then you have very cool water or chilling water through the chilling valve, okay? Then you do the heat exchange with the air. Then the cooling tower has the fan, okay, rotating, okay? Then the air will passing through here, okay? Then this is the cooling water, go back to the chiller to cool down again, okay? So the cooling water will absorb the heat in the air, okay? Then becomes warm again, then go back to the chiller to be cooled down, okay? Basically, you're using the water and air heat exchange. Okay. Then the electricity is consumed to reheat the water or cool down the water. So this is a typical structure of an air handling unit on the floor. Okay, it's a very big guy. So what does the air handling unit do? First, it has the air damper. The air damper is here. Usually, we will close up the damper for exchange air between the outside environment and the inside room. Okay. But sometimes we will open it to do the air exchange. For example, we can pump using this air pump to pump the air to the outside. Okay. And have the pump here to draw the air from the outside to the inside. Okay. Then once we have the air from the outside to the inside, and this is the heating coil, this is the cooling coil. If we want to warm up our room, and this heating coil will be turned on and operated. Otherwise, it will be turned off. And the cooling coil is the air conditioning function. Okay. So the air passing through the cooling coil and to be cooled down. And this supply fan, supply air pump will pump the cooling air, okay, to the different rooms. Then the room air will be taken back, okay, by this exhaustive fan, okay, or some exhaustive pump, air pump, to absorb the air in the room back, okay. So it can be directly exhaust the air to the outside or mix the air with the outside input air. And this is also called, there are different operating strategies. So basically in the summer, we will typically turn off this air exchange, okay, make it as a minimal level to make to minimize the air change, because in the summer the outside is very hot. We typically use the economizer, just do the internal air circulation. Okay, but in the winter we will do take a little bit more air in the winter. Okay. And the next thing is the VAV box, variable air volume box in each of the room. So besides the heating in a HVAC system, besides the heating and cooling coil, which is the major temperature controller in a building, then in each of the room, you also have a thermostat and a tiny right to adjust your room temperature. Okay, so you will now know that now all the temperature control is centralized based on the HVAC system. Then how can you determine your own room temperature? Then this is rely on the VAV box. Okay. So this is called variable air volume box. So you have the air from the air handling units. You have a damper to control whether you need to take a lot of them. Then you have an air diffuser. It is not here, but in some of the office, you will see such kind of air diffuser. We do have some, if you look at, okay, the top. So the next thing is it can use electricity to reheat or kind of, for example, if the temperature is too high, then we can actually increase the air volume. Okay. to using as a fan function to make a room temperature cool down. But if the temperature is too low, then we have a coil to using electricity to reheat the air to make it warm. So every HVAC system has a condition monitoring system to record its data. Okay, this is kind of interface of how the data recording in an HVAC system. All right, so we will stop here and take a break, and come back and finish the remaining slides. Okay, let's come back and continue. All right. So we have talked about basically the from the physics aspect about the how the HVAC system is operated, and then based on the data collected in this condition monitoring system, then what data scientists can do in conducting the HVAC research. So we start from learning the domain knowledge, analyzing system from the physics side, and conducting experiments for collecting data, and next going into data analytics. So basically, we can better model the HVAC system by using data and do a more accurate, more adaptive optimization of its performance. So first, let's look at a physical system of HVAC research in the first paper. Here we are going to introduce 4 papers. So in the first paper, it studies an HVAC system in charge of the heating and cooling jobs in this space. Okay, this is actually an energy research center space. So it has 2 classrooms and 2 parallel air handling units, mechanical room, and it needs to charge 1 computer center, 1 office, 1 display room, and the media center. So basically, we are actually using 1. So you can see that it's able to do a parallel comparison. We have 1 interior A and interior B, and West A, West B, East A, East B, and South A, South B. These 8 rooms being charged with these 2 same model air handling units, air handling unit A and air handling unit B. So we're collecting data of one of the air handling, both of the air handling units, and do a data-driven research to optimize the performance of one of it and test it parallelly, compare it with the another traditionally controlled air handling unit and see the improvement. So first we do design of experiments, because the thermostat's response is very slow. And traditionally, people don't prefer to change the settings of the HVAC system control. So if you look at the traditional condition monitoring system collected HVAC data, they don't bring much values because their values seldom change. And you are facing different columns of almost constant numbers, okay? So they are not valuable to do a research. So we are actually first design of experiment to help the operator to change the settings of that HVAC control to collect more data, describe the change of its dynamics over time. Then we do the data collection. So we collect 3 data sets. 1 data set is utilized to do parameter selection and algorithm selection. And the second one to do the training, and last one to do the testing. So to model one HVAC system energy consumption performance, we're actually using a boosting tree to select the most important features affecting the energy consumption of that HVAC system. So important features selected including the chilled water temperature and the solar normal flux, that's the outside condition, outside air temperature, cooling coil, entering air temperature, and so kind of. So it indicates that the system is operated in summer. So majorly, we consider about the energy consumption in the cooling process. And the energy consumption definitely decided by 2 parts. One is the outside condition, and another is in-room thermodynamics. So we consider those important parameters as the inputs, and we divide them to two chunks. One is controllable, one set of parameters that are controllable, including the internal loads and supply air temperature set point. Okay. So internal load typically reflects, for example, it's discrete, reflects like how many occupants in a room. Okay, whether the whether lighting conditions is high, medium, or low, also kind of. And supply air temperature set point and static pressure set points, they are corresponding to the cooling control. Okay, and you have other related in-room cooling and outside temperature conditions. We try different types of regression algorithms to mapping those input parameters and the energy consumption of the HVAC system. You can see we do have some of the regression tree models considered here. Okay, we consider a number of attributes to measure the performance of that model, and we find out the multi-layer perceptron ensemble actually serves the best in such kind of energy estimation, energy consumption estimation. So we actually do the individual subcomponent energy consumption, and to do the modeling, we estimate the chiller energy consumption, the fan component energy consumption, the pump energy, and reheat energy consumption. And we develop corresponding data-driven models for those parameters. Okay, and this is the visualization of the results. So you can see the estimation is pretty accurate. Then based on these 4 types of energy consumption models, we do a kind of optimization model formulation. So it integrates 4 types of energy consumption model as the objective, and do the control of the controllable parameters via heuristic search. We apply the particle swarm optimization algorithms. Then here it shows the energy saving. We can save some of rooms of the energy consumption, and also the settings we recommended. So we recommended more variable settings than the traditional, very stable static settings. We find out that could result in more energy savings. Okay, and this is the comfort condition. This is settings of other components, and also the energy consumption of the fan components. Okay, so we do a bar chart to compare the energy consumptions of different components and their corresponding comfort conditions. We can find that after optimization, we actually don't lose in much comfort conditions. Okay, slightly increased humidity, temperature almost the same, a lower CO2 percentage. Okay, so the first work is related to the energy consumption minimization of a HVAC system via data-driven model. And the second research referred to the chilling process optimization. Okay. First, we consider a very important ratio, which is called chiller part load ratio. Okay. So which is in between the chilling quantity and the chilling load, and also the chilling contribution. So the power and the chiller part load will be traditionally described as a kind of polynomial form. Okay, based on such kind of ratio with a square and cube term. And the cooling load is described as here. Okay, and this is also the physics expression. The temperature difference multiply the mass and multiply the coefficient. Okay, we actually can do the data-driven approximation of such kind of cooling load and process. Okay, so we build up 3 objectives based on the data-driven model to describe the actually these 3 chillers in a chilling plant. So it includes three groups of parameters. And in some of them, one is the dynamic states, the historical records of the chilling and energy consumption, and also the controllable parameters as X and non-controllable as V here. So you can see this is a kind of schematic diagram of the air handling units. And you will see we have introduced it. We talk about the return fan, supply fan works, and how the air passing through the cooling coil to do the chilling. Okay. So what involves here is the chill water coil valve position. The controllable parameters include 3, the chill water coil valve position, and the supply fan speed. Okay. And other temperature and outside air temperature and chilling water temperature, they are actually conditions we cannot affect much. So the 3 data-driven models include, one is cooling outputs, which is the estimation of the cooling load. So it includes its past cooling load records and set of the controllable parameters, including the chilled water valve position in the past historical states, and also the supply fan wind speed. And the supply air and supply air temperature and humidity are the second and third objective. So for modeling a relationship between the targets and the inputs, we apply a number of machine learning algorithms here, and we find out in multi-layer perceptron, NN is the best. So this is the visualization of the model accuracy. We can see that our models can do very accurate estimation of the targets. Then we do the similar optimization model formulation. Consider the 3 data-driven models as objectives. And we reformulate it as a multi-objective optimization problem and apply heuristics to solve it. And here is the cooling outputs optimized and observed, and the settings recommended and optimized, and the original, and also another controllable parameter setting, original and recommended. Okay. This is the air temperature, the original air temperature, and we can maintain in a more stable level. And the humidity, we maintain similar. So the previous talk about the cooling load modeling and energy consumption minimization. And next we talk about the heating part, the steam load modeling. Okay. So what needs to be considered in a steam load modeling? We consider the total steam load per day measured, and temperature, mean temperature of the outside air, standard deviation, and the max value of and minimum value of the outside air, and also the humidity. Okay. We do the correlation coefficient among those parameters, as well as using a boosting tree to measure their importance from a nonlinear perspective. Okay. Then we do, after do feature selection, we actually consider 4 scenarios of the feature selection. And it's based on different season. Okay, scenario 1, scenario 2, scenario 3, scenario 4. Find out each season, the model will have different dynamics and needs to select different features for developing model. Okay. We actually then, based on each of the month, we also do the modeling and see whether it can be further improved. We develop the AM ensemble model, and which will offer the best performance. So this is the observed and predicted value of different parameters, including a steam load in different date and different season. Okay. And the last research in the HVAC systems is about the modeling and optimization of the chiller plant. So this includes the operating of the chiller plants, turn on and off, and its control settings of the chiller plants. So we consider two types of factor. One is the electricity price fluctuation over time, okay, because we are going to consume electricity, and different prices of the electricity charge becomes important. And as well as the demand of the cooling load of a typical day, they actually follow a similar pattern. The plant operational costs will be estimated based on the power consumed multiplied the load estimated. And also X is a binary operating parameters include the on and off. And the PT here is not power consumed, it's electricity price. Okay. Then we can calculate the total cost of operating the chiller plants. So here we have 4 chiller plants, and different chiller plants, they have capacity of chilling water process. So the first and second one can handle 3,000 tons, and the third and fourth one can handle 2,577 tons. And the parameter name of those chiller plants is presented here. It includes the cooling load produced, the power consumed, and the temperature difference between the condensing water. Okay. Then we do parameter selection and do the modeling for each of the chiller plants and compute the error of the data-driven modeling performance. Okay. Then we formulate this optimization model, and we introduce a 2-level intelligence algorithm to solve such kind of non-parametric and data-driven optimization model. And this is the visualization of our modeling performance, including the observed value, which is the data we observed, and the estimated based on our data-driven model. It's pretty accurate. And this is a kind of optimized results. It's a kind of operation planning of the 4 chillers. Okay. And blue indicates on and red indicates off. So it sounds like the chiller 3 is never necessary to be turned on. And we will intend to operate more on the plants that have been operated. Okay. And this is recommended cooling load to be processed by each of the chiller that day. And we can save significant power consumed by chilling plants via the optimization. Okay. So actually, here we would like to share is actually the data-driven model offers a new dimension of studying the dynamics of such kind of complicated HVAC system. And it offers a very nice approximation of the system performance. And based on such kind of data-driven model, we are able to explore more potential of energy saving via the better and more dynamic optimal control of that system. And what else for the real implementation of such kind of big data and AI techniques for HVAC system? So first, nowadays, we need to consider the energy internet and energy system integration. For example, in the previous studies, we never considered buildings integrated renewable energy systems, and as well as electric vehicles. There are new characters in such kind of energy supply and consumption scenarios. And second, we want to make the energy saving into economic measures. So we need to have smart meters to measure the energy supply and energy consumptions and their flows from time to time. Okay. And we need to have a cloud computational services to centralize the data and to build up data-driven models, which will serve as a backbone to be easily adapted into different applications. And we need to have real-time responses of the HVAC system operation for energy saving. and also to touch the interactions with the power grid. All right, so today's lecture we will start here. Okay, then the remaining time, yeah, so basically these lectures we talk about the applications of data-driven techniques. We hope those application stories can help you guys to better explore and do your class projects. Has nice examples of do your projects. You will see how you have seen like how these data collection to modeling, problem analysis, and finally generating results work. Okay. And yeah, so we will stop here, and the left time you guys can do your projects and spend on other places. All right, so next week we are going to start our project presentation, and we will do that via the Zoom online mode, so we don't necessarily to do a face-to-face meeting, okay? And it will be very convenient, more convenient from the Zoom. All right. Okay, see you guys next week. Bye-bye.